All right, ladies and gentlemen, this is chapter 37. We'll get this done in one part instead of two. But what we're looking at today in chapter 37 is electromagnetic induction. And with electromagnetic induction, basically the main point is you can take magnetism and make electricity. You can take electricity and you can make a magnet. And so this has a lot of things to it that, deal with stuff that happens every day. The generators that we see in Shasta Dam are basically, you take a magnet, you spin it around, and you make electric current. When we look at those electromagnets like that were on the crane thing that was grabbing the stuff at the junkyard from the last chapter, you are taking electricity, passing it through, and creating a magnet. And so this idea that magnets can make electricity, electricity can make magnets, the key point is all we've got to do is change what the magnet is doing to make electricity, and we've got to change the what's happening on the electric end to create a magnet. So basically, Michael Faraday and Joseph Henry both sort of independently discovered this at the same time. And their discovery changed the world because it, again, creates the power that essentially lights all of our cities anymore. And if you look at the year 1831, over the next 20 years, they kind of perfect this process. And the key to starting the Industrial Revolution around about 1850 is that you can power your factories 24 hours a day now. And when you can do that, you can work people all day long on these, never-ending conveyor belts and things like that, because they have power and the employees can see at night in the factory. And that is sort of what leads to, again, that Industrial Revolution. So electromagnetic induction just says that if I have electric current, it can be made in a wire by moving a magnet into or out of a wire coil. And so if I just take this magnet, move it up and down inside of the coil, we generate this electric current. In the generators out at Shasta Dam, basically what they're doing is they are spinning a magnet around, spinning a coil of wire around a magnet, and this creates the electricity that comes down into the valley from Shasta Dam. But no battery or other voltage source would be needed to produce current anymore. It became unnecessary to have a battery. The only thing you need is the motion of a magnet inside of a coil or wire loop. Okay, it's got to be moving. If that magnet is sitting still, the magnet is in the person's hand, it won't generate any kind of electricity there. But voltage is induced by the relative motion of the wire with respect to that magnetic field. The production of voltage depends only on that relative motion of the conductor with respect to the magnetic field. And so voltage is induced whether we take the magnet and move it up and down the wire. Again, it's got to go up and down this way. If I try and move it parallel with the wire, it's not going to have any effect. We've got to move it perpendicular to it. Or I can take the conductor and move it up and down inside of the magnet. Either way is going to generate some kind of electricity there. The results are the same because the relative motion is the same. Now, the amount of voltage induced depends on how quickly the magnetic field lines have been traversed by the wire. So if we move the wire or the magnet very slow, we're not going to produce very much voltage at all. If we move it much quicker, we're going to get a much greater voltage. Another thing we can also do is increase the number of loops of wire that move into and out of that magnetic field. And this will help give us more voltage and more current in the wire. The other thing we can do is push the magnet into the same number of loops, but move it twice as fast. Okay, so twice as many loops or twice as fast is going to give me twice as much voltage. And so here I have my magnet. I'm moving it up and down. With 2 loops, I'm going to generate half as much as the 4 and 1/3 as much as the 6 loops over here on the right. So 3 times as much as this one, twice as much as this one is going on there. Now, we don't get something for nothing here, okay? And that something here is electrical energy. So if we increase the number of loops, basically what happens is it gets harder and harder to push that magnet. Now, this is a system that we call a butter churn method for generating electricity. What the lady's doing here is holding a magnet, and she would then thrust it up and down into this coil here, and it would generate electricity. You could generate enough electricity to light your room, but it means somebody's got to be moving, and somebody else would have to then do the cooking while this person was generating the light. So it's not terribly efficient, but it does work. And why they call it a butter churn, I think is pretty obvious, because the loop here kind of looks like the churn, and this is the rod that you would mash the cream up with to create the butter. So if you try to push a magnet into a coil with more loops, it just requires more work to push and pull on the magnet. And so here we have pushing in. Well, when we push in, basically what it acts like is a repulsion, is that north and north are acting on each other. So it is hard to push it in because of the repulsion. And then when we try and pull it back out, basically what happens is the magnet in the coil switches direction and becomes south-north. And so the north is attracted to the south, but we're trying to pull it away. And so when we're pulling that away, we have to expend energy to do that because it wants to be together. So the law of conservation of energy applies here. The force you exert on the magnet multiplied by the distance that you move the magnet is your input work. And this work is equal to the energy expended or possibly stored in the circuit to which the coil is connected. If the coil is connected to a resistor, more induced voltage in the coil would mean that there's more current through the resistor. And that means that you're going to have to expend more energy to make it happen. So inducing voltage by changing this magnetic field around a conductor is what we call electromagnetic induction. And what it boils down to, again, and we'll see this a little bit in 37.7, our last section, that we can move an electric field around, and in doing so, we generate a magnetic field. So how can you create a current using a wire and a magnet? Again, you have to have some kind of relative motion of the magnet about the wire. It does have to be perpendicular, can't be parallel, or it's not going to have anything happen. So the next thing we're going to look at here is Faraday's law. Faraday's law gives us a mathematical way to figure out how much electricity or voltage is going to be generated. Now, we're not going to do a lot of this math for a pretty good reason. We're not going to actually find the voltage because while it's relatively easy to find the number of loops and the cross-sectional area of the loops, this rate at which the magnetic field changes, which we call the magnetic flux, can take some calculus to figure out, and where most of us are not there. So anyway, voltage is just proportional to the product of the number of loops. So more loops, more voltage. And then the cross-sectional area of each loop, bigger loop, is going to give us bigger voltage. And then the rate at which the magnetic field changes, basically the rate at which the magnetic field changes, again, has to deal with how fast we're moving the magnet. How fast are we changing what it's doing? And so this, again, as I mentioned, is called the magnetic flux. And so how fast that changes does allow us to make the induced voltage larger. So Faraday's law describes a relationship between induced voltage and the rate of change of a magnetic field. And so the induced voltage in a coil is proportional to the product of the number of loops. So again, more loops, more voltage. It's proportional to the cross-sectional area of each loop. So bigger loop, you're going to have bigger voltage. And then the rate at which the magnetic field changes within those loops. So again, how fast are we moving the magnet? And so you think about those generators out at the dam. What they're doing is they're getting those suckers spinning really fast by driving water through them. And when you drive the water through them, spin them really fast, you're getting a bigger change in that magnetic field per time. So that rate goes up. So current produced by electromagnetic induction depends on induced voltage and the resistance of the coil and the circuit to which it's connected. So again, this goes back to V equals IR, Ohm's law. So for example, you can plunge a magnet into and out of a closed rubber loop and in and out of a closed loop of copper. Which one's going to have a current flowing through it? Okay, well, both of them are going to induce a voltage. The problem is with rubber being a insulator, it is not going to move those electrons around very well. And so you're going to see the movement of the magnet be relatively easy. But you do it in copper. Copper is going to provide a conductor for those electrons to move. So you thrusting that magnet into and out of that loop of copper is going to take a bit more work. And that's because you're going to cause those electrons to flow. So if you push a magnet into a coil connected to a resistor, you feel a resistance to your push. For the same pushing speed, why is this resistance greater in a coil with more loops? Well, more loops is going to create more voltage. More voltage is going to have more current for the same resistance. And so basically, it just boils down to the fact that you're going to have to do more work in order to get more of the current to move around. So what does Faraday's law tell us? The voltage in a current carrying wire is going to be proportional to the area of the loop, the number of loops, and the rate at which the magnetic field changes about those loops. All right, and so our last section, 37.7, is basically a consequence of Faraday's law. Something that Faraday kind of recognized early was that, wow, I can use magnets to make electricity, but I can also use electricity to make magnets. And so 37.7 just tells us, hey, a magnetic field gets created in any region of space where we change the electric field. So if we start moving the coil around now, we are going to create a magnet. And so electromagnetic induction has been discussed solely in these first two sections pretty much as producing voltage and current. We're talking about production of electricity. But if we look at it in a more fundamental way, it's better to look at it in terms of the induction of an electric field. And so we make these electric fields, and when we make those electric fields and we are moving the magnet around and things like that, that gives rise to the current and the voltage. But induction takes place whether or not we have a conducting wire present. And so Faraday's law just said that an electric field is created in any region of space in which a magnetic field is changing with time, and the magnitude of the created electric field is proportional to the rate at which that magnetic field changes. And if the direction of the created electric field is at a right angle to the changing magnetic field, this all happens. Again, doesn't happen if it's parallel. Has to be right angle or perpendicular. So if the electric charge then happens to be present where the electric field is created, this charge is going to experience a force. And for a charge in a wire, the force could cause it to flow as current, push the wire from side to side, okay, as we saw in the second half of 36 notes. But for a charge in the chamber of a particle accelerator, the force can accelerate the charge to very high speeds. If we get it spinning around and around and around and around, and we keep kind of tightening the noose, if you want to think of it that way, of the magnetic field around it, it can get it going faster and faster and faster. But there is this second effect, which is the counterpart to Faraday's law. And it's just like Faraday's law, but it's kind of all we've done is reverse the roles of electric and magnetic fields. And what it says is that a magnetic field is created in any region of space in which an electric field changes with time. So the magnitude of the magnetic field is proportional to the rate at which the electric field changes. If I move the coil around faster, the magnetic field is going to be bigger. And the direction of the created magnetic field is going to be at right angles to the changing electric field. And so how can an electric field create a magnetic field? Electromagnetic induction. Again, the magnet can create the electricity can create the magnet. Now, where 37.8 goes, we're not going to get into it, is that further study showed us that electricity and magnetism were so intertwined that they create electromagnetic radiation. They create light. And so if you want something that's kind of interesting to look at and show how electricity and magnetism tie to one another and create that electromagnetic radiation, again, it's the magnet is creating the electricity, which creates the magnet, which creates the electricity. And this changing of magnetism to electricity is what makes light. And so something that's kind of interesting, little side light there. But this is it as far as the book notes go for the year. I do have one quick little video that I'm going to put out, has to deal with something called the right hand rule. But other than that, if you have any questions, twyrick at auhsd.net. Have a great day.